sometimes in our applications we are using an emulsifier. But here you will see that there are some hydrocolloids, polymers that can act as an stabilizer also. So here you have the a general definition of nanoemulsions. Nanoemulsions consist of at least 2 immiscible liquids, usually oil and water, and one of the liquids is being dispersed as small droplets, 100 nanometers in the other. The potential advantages of nanoemulsions. You have one of the most common advantages, the high stability. We will increase the stability of that nanoemulsions. High surface to mass ratio. It means that if we reduce the size of that nanoparticles, then we will be able to improve lipase activity, for instance, the digestion, and then also the functionality of these compounds. That nanoemulsions can be more transparent, so this is good for food applications. And also they have some novel texture properties depending on the formulations. One method to prepare these nanoemulsions are the microfluidization. The product is separated in 2 streams in the equipment you have here. The product is separated in 2 streams so that they collide each other at high pressure, creating high shear forces and causing the breakdown of the particle. Okay. Parameters we can control are the pressure and also the recirculation cycles. There are some equipments you can control the temperature also. We are trying to improve the incorporation of lipophilic compounds. Here you have some of the bioactive compounds that are quite interesting: fatty acids, carotenoids, antioxidants, and so on. These compounds generally have some difficulties to be introduced in food matrices because of the low water solubility, because they can be easily oxidized, because the viability of these compounds is quite low in food matrices. So this is the nanoemulsions can improve, okay, the incorporation. We will focus today on beta-carotene. Beta-carotene is a lipophilic molecule with vitamin A activity. You know that we can find beta-carotene in fruits and vegetables in general, and it's related with health properties. This compound can reduce the risk of certain cancers, cardiovascular disease, and other pathologies. Here you have the gastrointestinal fate of that droplets, oil droplets. They can suffer some desestabilization phenomena in mouth, in stomach, but the major change will occur in the intestine phase, in the small intestine. The droplet, the oil droplet, when it arrives to the small intestine, bile, salts, other molecules with surface active can replace that emulsifier, that is the shell of the oil drop. Then the lipase, you know, it's absorbed on that oil surface and start the lipolysis of fat. Then the beta-carotene is released and is solubilized with micelles. We know that large mixed micelles are improving the bioaccessibility of these compounds. This is one of the factors we know that is affected. So what's happened if we incorporate these beta-carotene in the nanoemulsions. This is one of the objectives of this work. You have here, we tried to design nanoemulsions as delivery systems of bioactive compounds, the beta-carotene specifically, by studying, in one hand, the physicochemical characteristics, and on the other hand, their potential functional properties. We will study the digestion and also the bioaccessibility of beta-carotene. In the formulation of nanoemulsions, the formulation consists on mixing at least 3 compounds: oil, water, and also the emulsifier or the stabilizer. Okay? In our case, we use corn oil, and we, first of all, enrich the beta-carotene to this oil at concentration of 0.5%. With this enriched oil, we prepare emulsion with oil, with this oil, with the surfactant, is a non-ion surfactant, 20, but there are a lot of them, and water. In some formulations, we use also a polymer, a pectin, and high methyl esterified pectin in some of the formulations. Then we prepare two different nanoemulsions. The large emulsion is the one that we call as conventional emulsion, the one that is just prepared with high-speed blender, and the other one was the small emulsion or the nanoemulsion, the one that is prepared with, by microfluidization. The factors we studied here were the lipid carrier concentration. We had 2 different systems, low fat and high fat at 1 and 4%. Surfactant concentration, this is was the second factor. We had 3 different systems, a low, medium, and high, 1, 2.5, and 4% of the surfactant. And at the texture modifier, concentration was the third factor, a low pectin system, and another we call high pectin, 1 and 2%. We studied, on one hand, the physicochemical characteristics by studying the droplet size and the zeta potential, the emulsion color, also the viscosity, and we finally studied the oil digestibility and the beta-carotene bioaccessibility. We simulate an in vitro small intestine digestion with bile salts, calcium chloride, and lipase, and we determined the lipolysis rate based on the percentage of free fatty acids that were released during that digestion, and the beta-carotene bioaccessibility determination was calculated based on the concentration of beta-carotene in the initial emulsions and the concentration of beta-carotene in micelle phase that was obtained by centrifugation of the digestion sample. Sorry. Here you have some of the results, because I can't have time enough to show you everything. Here you have the results for the emulsion droplet size. You see, in all graphs, we'll see there's 2 systems. So, 2 systems, the low-fat nanoemulsion systems and the high-fat nanoemulsion systems. Here what we saw is that the higher the pectin concentration in the nanoemulsions, the greater particle size. Also, that we increase the concentration of the surfactant of the emulsifier, we reach lower particle size. Here you have the distribution of particle size, and here you see samples with 2% of pectin and 2.5% of T20 presented the highest particle sizes. So the pectin, the addition of pectin, will substantially impact on the particle size. We were, in all cases, in the nano range. I mean, we reach particle sizes low enough. Okay? So our droplets were small. Here you have the emulsion, the zeta potentials. This is an indicator. It gives us an idea of the electrical charge on the oil surface. Okay, so generally we know that values lower than minus 30 millivolts or values higher than plus 30 millivolts gives us emulsions stable enough. Stables for some days at least. Okay, but this not was our case. I mean, here you see that nanoemulsions without pectin showed values around minus 20, minus 25. And visually, we show that we're stable just for 12, 15 hours. Okay? The addition of pectin in that emulsions give us potentials, higher potentials, minus 10, minus 5. So it's supposed that nanoemulsions were not stable. But visually, and because we kept that nanoemulsion in the fridge during days, we saw that were stable for 1 week. And because we didn't check more days. So we know that an increase of the viscosity in that nanoemulsions gives us stability. Because it's supposed that we minimize the movement of oil drops in the aqueous phase. Okay? Here you have the viscosity. Of course, we saw that the viscosity is related to the addition of pectin. So the more viscous samples were those with pectin. And about the color, okay, to be fast, just saying that the more, as we added more oil, we obtain more clear nanoemulsions. Whiteness index is an indicator of the milky appearance of the nanoemulsions. We know that low values of whiteness index give us an idea of the transparency, because it seems that, the nanoemulsions scatter the light intensively. In our case, the nanoemulsions with 2% of pectin give us more transparent nanoemulsions. But we studied also how reddish were the samples. And here, the most relevant, of course, if we add more oil, it's because we are adding more beta-carotene, so the samples are more red. But if you see here, nanoemulsions with 2% of pectin and 4% of oil were substantially less red than the others with 1%. So are more transparent and less red, that can be good for some applications. We don't know, dependent. Okay. And then finally, okay, we didn't detect any difference in the digestion of different nanoemulsions, with pectin, without pectin, with more or less surfactant. Okay? But the bioaccessibility was increased in those prepared with pectin, 2% of pectin. So the pectin can protect our compound during the digestion process. And finally, this is the last slide for the results, if I give you a comparison of nanoemulsions and macroemulsions or conventional emulsions, what we saw is that nanoemulsion is rapidly digested and can affect to the bioaccessibility. You see, nanoemulsions are more, the beta-carotene and nanoemulsions are more accessible. Okay. The conclusions then are the following. Okay, we will reduce the particle size of the nanoemulsions if we increase the quantity of surfactant. But be careful, because an excessive surfactant can decrease substantially the bioaccessibility of the compound. This is what we said. Stability. The more stable nanoemulsions were those containing pectin at 2%. Okay? Those that nanoemulsions were more bioaccessible to the body also. So these are the main conclusions. We don't have time, so I think that it's enough. Okay.
Presentation. However, coming to consumer views, nano may be the new GMO. When you ask consumers in various countries, 80–85% say they don't want food with nano scale material inside. So it might be a communication problem occurring again. Any ideas on that matter?
I completely agree with you that this is the main problem for the application on food of that kind of nanoemulsions. But I think that the question is to communicate well our results, okay, in a clear way. And what we know, I don't know, because I haven't time enough to show you better the results, but if you see, for instance, in our applications, the digestion was like over 80–90%. So it means that everything, or almost all the oil is digested. So in that case, there's no problem. I mean, everything that will pass for the intestinal cells is free beta-carotene. But we know that there are some studies that have used that kind of application on liver cells, for instance, and they saw that the viability of that cells are really reduced. But the key is that we need to reach completely digestion of our nanoparticles before getting into the system.
Then there might be the consequence that there is a regulatory problem occurring, because if you have a substantially different, better bioavailability, this will apply the novel food regulations. So you will have to ask for permission of this new technology and this new properties, and walk through the registration process again.
Okay, I agree, but we are in the first steps. I mean, in our studies here, we don't have results about toxicology studies, but the project, because this work is enclosed in a big project, that studies are also covered. So we are on the first steps. Then when we had the final results, then we can develop new